So in the process control charting, we want to find that variable that can indicate the performance of the whole process. So measuring a mass on a scale, which is the foundation of your whole operation, because you use mass to calibrate your volumes and use volumes to make up your concentrations and so on. That's at the very bottom of your process. It's really important, but it doesn't give you any information about how the GC is operating. So it would be better if you have something in the GC that's you're monitoring, and if it stays in control, that means everything below it is operating at least within an envelope of acceptability. Does that mean the balance hasn't changed? No, but it hasn't changed to the point where it's throwing the whole process off. Okay, so with that one process control variable at the end, you can kind of get the whole pyramid, and you can tell if the whole thing is shaken or not. Now, it does make it a little bit more difficult when it goes out of control, because then you got to figure out what part of the process is broken. So you may pay later, instead of having 5 different checks on the balances and the volumes and this and that, where you would know instantly that the balance is crazy. You're checking the end of the process, but if the end of the process is good, then the whole system's within the envelope of its variability. And so that's ideal. So it's unchanging if the process is unchanging. So that's why we don't want to, for our control charting exercise, we don't want to pick something that's changing as the semester goes on, like temperature. Okay. We want something that ideally has a mean value and only changes a little bit around that mean. So we have the regular, everyday, random variations around the mean, and that's what we mean by unchanging. It's got a stable mean over time. Okay. But then this doesn't, nothing is ever exactly the same. So it's vibrating or moving around up and down with random variations. Okay. So that if something non-random happens, then we know a significant change has happened. So there's only a 5% chance that this change would have occurred. So we start investigating. We start seeing if something changed in the process. Maybe the tank is going out, the GC is pushed along by gas, the carrier gas. It could be the balance, probably not the balance, probably is the tank, probably something, maybe the flow rate controller, maybe you've got an equipment failure. Maybe you got a different source of your compound and it's changed in some way. But anyway, it's time to investigate. So in terms of our 15 data points, we're not quite there yet. Everybody has, some data points, but when you get to 15, remember to do your daily differences the correct way. And when you have 15 days, you're going to calculate the mean and the standard deviation. Now, one thing that is a bit confusing to folks is you don't recalculate the mean every day. You calculate the mean of the first 15 days, and then it's fixed the rest of the semester. So the 15 days is what we call the training period or learning period. So we're learning about our process. Right now, we don't know if our process is in control or not. So we're going to go for 15 days and calculate the mean and the standard deviation. And then that will be, we now know our process. We know how it varies over time. And then we're going to track our data the rest of the semester and see if it stays in control. So that's what we're doing, okay? And so be sure to use the standard deviation .p. That's the population standard deviation, and then average is the average. So, daily change, temperature, pressure, pollen, all these different things, stock prices. There's this normal daily fluctuation in the process that produces these data, okay? When it goes more than 2 sigma above or below the mean, something significant has happened. So you need to research it. Sometimes it's so significant that the data disappears. One year we had it was a few years ago, but we had a student tracking Yamaha stock, and it's a Japanese company. And sure enough, the Fukushima power plant blew up, nuclear meltdown, tsunami, earthquake, all this stuff. And their stock exchange went down for several days. So he's like, what do I do? There's no data. I was like, your system's way out of control. You write that in the log, it's like no data because of an earthquake, a tsunami, and a nuclear meltdown. Certainly easy to research. You go to the news, you're like, what's happening in Japan? Oh yeah, everybody knows. So that's interesting. That was an easy one to research. Okay. But let's talk about the philosophy behind control charting. I think this is the main point for today. It uses this Japanese concept called Kanban or Kanban. And you can look this up in Google and see all kinds of little charts and stuff like that. This is not just for scientific information. This is just a process, what we call a best practice in any kind of manufacturing, any kind of business, even human resources or accounts receivable. In various companies, they'll use this same kind of thing. They'll have a key process variable that they track. It might be number of orders per day or something like that. And they'll say, wow, something's going on. Our orders per day were pretty stable. And then all of a sudden they drop off. What's happened? And so management doesn't want to go in and meddle with their operation until they see something significant happen. And so this might be a key process variable for their little division. And a lot of times management wants to have like a dashboard for the company. We had that at Pantex. We had to decide as a department what our key process variable would be for the whole department. So that's not even like a GC or a balance. That's the whole department. What single number could tell our management that our department was feeling pain in some way. Okay, and so we had meetings and we figured it out so that the every day the general manager could have his chief of staff pull up the dashboard for the whole company and say, oh wow, the chemistry lab is in pain. What's going on here? There's something out of control. So this is not just in the lab, but it happens across all businesses. And this concept of Kanban or Kanban is this idea. Well, let's talk about not using it first. Let's say you're in the lab and you said, okay, we're going to calibrate it every morning. We're going to calibrate our GC. Okay, that's a schedule, and schedules work on a push. So it's a new day. Guess what? You're being pushed to calibrate because there's a schedule. Have you analyzed the system? Is it still stable? No, because you don't care about the system. You care about the calendar. So the calendar is pushing you to do things. Maybe you calibrate once a week. Maybe you calibrate every day. But it's the calendar that's pushing you, not the system. Okay. Whereas a Kanban or Kanban is a pull philosophy. The system itself is telling you when to calibrate. So if we're tracking this process variable and all of a sudden it goes out of control, maybe it was in control for 7 days or 8 days, something other than a week, right? And then all of a sudden it's out of control. It says, all right, let's do a calibration. So the process itself tells us when to take action. And the same with the manager's dashboard. He's not going to fiddle with every department in the whole company. He doesn't have time to do that. But all of a sudden something shows up on the dashboard. It's pulling his attention to go do something. That's what this means by pull philosophy. Kanban is a sign. So it's a sign that pops up and it draws your attention and pulls your action to take action. So that's the pull of the control chart. We look at this control chart, and whenever something goes out of control, that's a Kanban. That's a sign that action needs to take place. We do this naturally. It's your check engine light. Okay. And that's a great example of picking so many variables that it comes on and yet your car still runs just fine. So are you motivated to go, ask them that some tiny little, sensor is giving you a bad signal and you're like, maybe if I wanted to keep my car running perfectly, but I know if I go into the dealership, they're going to find 5 more things that I need to fix. It's going to cost me a lot of money and the car still runs just fine. So they've kind of diluted that signal down to where, the check engine light is almost, it's easy to ignore. So just get you some black tape and put it over. Probably not a good advice, but it's tempting. Okay, so this saves money also because it focuses on the problem, not the schedule. Because every time you spend time calibrating, you're not running samples, and time is money. That forensic scientist or whatever that we looked up was $35 an hour. So if it takes you an hour to run a calibration, it costs you $35. And did you get any more throughput on your backlog? No. That's called overhead time, and not overtime, but overhead. It's spent on the business, not on the client, on putting samples out. So It gets expensive. You add that up. If you do that once a week, take $35 an hour times 50 weeks a year. So it starts to really turn, get up in the, and that's pretty conservative. Plus you have the chemicals and all of that too that you have to buy. It also improves quality because the performance is frequently monitored. So let's say you do the check sample every day, and that's your control chart variable. It doesn't take you an hour to do a check sample. You can put it in the tray with all your other samples, and you can see that check sample comes in and control, then you're ready to go with all the other samples, and it's just a few seconds, so it's insignificant in cost. The third thing it does is it reduces your standard deviation. It makes your uncertainty more narrow. Did everybody see, this dates me, but back, I think it was Prices, right? They had the little Plinko game, and they put a little puck in there, and it bounces through the pegs and goes down. That's a statistical tool called a quincunx. Quincunx. It's a weird word. C-U-N, I don't know if it's an X or a CKS. We'll say X because it's fun to say. Quincunx, okay? And that's the dots that the little ball goes down. And so the ball goes down, bouncing from pin to pin, and it ends up in these little bins down here. And of course, for the Price is Right, they had different, prizes down there. And sometimes you see this on the mall. I think the student activities has one for their various little Bearcat merch or something like that. Whenever I see it, I get all excited because it's a statistical tool. And what would happen if you dropped a ball 1,000 times into these bins? You'd get the histogram of a nice normal distribution. Okay. So what if you put the ball in there and it bounces down to the right? Okay. And you move this whole thing over to the right so that it's centered, thinking that the ball is going to hit there again. And you run it, and it goes way over there. What you've done is you've got the normal variability of the quincunx, the balls and the pegs, and you've added a factor of moving the bottom piece. And what that does is it adds 2 standard deviations in instead of 1. You have the standard deviation of the quincunx, and then you've got the standard deviation of your response to the quincunx. And it widens your uncertainty. It makes your process less precise. Over adjusting. So what would be over adjusting? Over adjusting would be calibrating once a week, whether you need it or not, because the or not piece. It may not need calibrating, and because the calendar told you to calibrate, you've moved these guys. You've added variability into it by the calendar. Whereas maybe your technique on whatever day you calibrated was sweet, perfect, narrow, and your instrument's working good. Don't wreck it just because the calendar. Wait until it tells you that it needs to be moved. Okay. And then you've narrowed your variability by taking yourself out of it and taking the calendar out of it, and you just let the system run. So you don't let it run blindly. You do your check samples. So you're still making sure that the ball is falling near the mean plus or minus 2 standard deviations. And then if it doesn't, if there's something significant, the ball goes ding, 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 bounces way over here. You're like, okay, there's an issue. You look, and all these other pegs are clogged for somehow. The analogy's failing, but it bounces all the way down here because it can't fit through the other pegs. That's significant. That's non-random. That's something has changed with the system. So that's the quincunx. I need to get some programmer to animate one of those for me, because that would be good in this class. Okay, so now this control chart, I just wanted to kind of show how this exercise that you guys have is a standard practice. This is the ASTM method for standard practice for using control charts. And I wanted to show you this because I don't know how much experience you guys have with standards like this, ASTM standards. But I've always wanted our chemistry majors to at least come through chemistry. You had one in the PChem lab, the RGB lab. It had an ASTM standard for determining the tristimulus values. So that process that we worked through in the RGB lab, if you went through that lab, you can write down on your resume familiar with ASTM E308 for determining the tristimulus values for a substance. Okay, you've done that ASTM. In this one, you can say familiarity with ASTM E2587 for control charting. That's a feather in your cap. Put it on your resume. That's something that employers can look at and go, "Oh, that's cool. Okay, they've learned how to control chart a process. I think that might put this candidate up a notch, and let's give them an interview and let's ask them questions." You always want to find something that can separate you from the other chemistry majors that are applying for the same job. Okay, so this is a good feather in your cap. It's on Blackboard, so read through it. I'll point out in red a few sections that I think are really important, but it's very easy to read. It first starts out with a scope. Why would I care about this procedure? Does it even apply to what I want to do? You can skim through the scope and say, yeah, it applies exactly to what we want to do. There's always, it's wonderful. These things are so well written. There's a whole section on terminology. So we're all using the same words the same way, right? It has like assignable cause. When something moves out of, there's the random cause variation. That's not assignable. I don't know what caused it to jump a little bit, but if it jumps 2 sigmas away, I need to look for an assignable cause. Can I assign that to something? The stock disappearing in Japan was assignable to the earthquake, the tsunami, and the nuclear meltdown. Okay. We have accepted reference values. We have certified reference values. We have standard reference materials. There's all kinds of different references. This accepted one would be an agreed upon reference. That might be your own internal library standard that you use. And so that would be your ARV. Now, this is when we talk about learning the difference of the goals of this control charting exercise. I say we learn the difference between continuous variable data and discrete data. Okay, and I still get students that confuse that continuously variable data with time. It's not that it's continuous in time that happens every day. That's not what we mean by the word continuous. What we mean by it, between 2 points, it can have any value in between 2 points. It's continuous. Discrete data means it's rounded to the penny. So it can't have 1/10 of a cent or 100th of a cent, right? So that's discrete data, and that's why we don't use gas prices, because those have been rounded and they're discrete. Okay. We talked about assignable cause just now. Also, there's many factors that contribute to variation, and it may not be feasible economically or otherwise to identify some of them. So, it may be an assignable cause, but sometimes it's just hard to figure out. And you're like, well, we know something non-random happened. We're going to take action, but we couldn't really assign it. That may happen to you guys if I'm trying to think of all the data that you're collecting. A lot of people are collecting temperatures, and it may not be something that you can find. You can say, I looked at the weather system, weather commentary or websites, and put in your action log the URL where you went. Okay, so that I can check on that. The one who's tracking temperature in Korea, I don't know what kind of research you're going to find. That'll be interesting to me to find. Like, we know here in the United States that people are obsessed with the weather. It's in every newscast at least 3 times. Have you noticed that? It's like that's the only thing keeping you watching the news. Like, they give you a little weekly forecast, and then they come back and talk about the fronts or something like that. And it's just the only thing that keeps people watching the depressing news. So it'll be interesting to see what happens in Korea when they have a temperature fluctuation that's not random. Okay, some other terminology. This chance cause, that's what we're reading by random cause. Incoherent random variation in a process, which is predictable within the limit. So if it's between your 2 standard deviations, that's where we expect that. And this is just the definition of the control chart and the control chart factor. So this factor is the data that you're collecting. Okay, and then we have the lower, and down here is upper control limit. So those are the watch limits are plus or minus 1 standard deviation, and the action limits are plus or minus 2. So if it's getting, it's just there to kind of give your eye a reference. If it jumps up it's one standard deviation away. It's a 63% chance, I think it's 63, but that it'll stay within plus or minus 1. So, if 100 measurements, you're going to have a lot. You have 37 measurements outside the one plus or minus 1. Okay. Or you'll have, roughly 4 out of 10. Okay. We also, this whole thing is under the umbrella of what we call statistical process control. It's a set of techniques for improving the quality of a process output by reducing variability through the use of one or more control charts, and then a corrective action strategy to bring it back within statistical control. But it's not, the important thing is it's not calendar based, it's process based. So when the process says my statistics are telling me I'm out of control, do something, fix the situation, then we take action only when we need to. Here it is again. So the upper control limit is obviously what we were talking about, the lower and upper control limit, but variables data, observations or test results defined on a continuous scale. So there's that word again. We're learning about this continuous data. It has to be continuous, not discrete. The reason I'm harping on that is because it's sad when we do this whole exercise, and then in the final report they say, I chose my data for temperature because it's reported every day. It's continuous, and it's like, that's where the hair went. That's not what we're talking about. It's not that it's reported every day. It's that it has, at any data point between two points, it can have ideally an infinite number of other data points. It's continuous on the data axis. There's a continuum of data points. Okay, and then significance and use. You could go through again the principles of statistical process control. That's really what we're talking about today. All processes have a certain amount of variability, and this standard is sort of helping you implement that. Look at all the variable definitions too. This is really wonderful because we can talk about all the different ranges and standard deviations and all of that. It's all well defined. So this is what you expect from an ASTM. They're glorious documents. Okay, it's a sad thing. If I was in charge of our whole chemistry curriculum, I would love to go into all of our labs and find places where we could give you one of these documents and say, all right, we're going to do this synthesis or whatever experiment or this analysis and instrumental, and we're going to use this ASTM on that process. And that way you would come out with like 15 ASTM methods that you've used. You may not be an expert in them, but you've at least been exposed to them, and you know what to expect from a well-written document. These things are much better than our little lab handouts, mine included, I confess. There's a committee that works on every little verb and noun and comma in these documents, and so they're well produced. And some of you may be those meticulous people, right? That it should be said better. It should be said better. And they're always like tightening the screw on how they document things. These committees you would just love if that's your personality, right? You would contribute in the future to these documents by serving on those committees, and that's something to strive for. It's great. And so then we have the different stages. Okay, the first stage is that learning stage where we're evaluating the stage. It says 30 data points should be collected. So we're not quite there. We're starting with 15. That's our learning stage. But we only have so many days in the semester. But ideally, they're saying go to 30 data points to get the historical average and standard deviations for your process. And then the process improvement, the data is collected in real time and so on. And this is, again, the team approach, looking to see what special cause variations might be susceptible to the process. And then the process monitoring. So we're doing stage A and stage C from the ASTM. Stage C is our process monitoring. So we're going to monitor our process. If something goes out of control, then we're going to take action. And our action is going to be really simple. It's going to be try to research what happened and put it in a log. We can't calibrate the temperature of Seoul, South Korea, or Huntsville for that matter. But we can certainly look in the literature and see, okay, this is what caused that point to go out of control, and it ought to reset because we're doing daily differences. Lastly, how do we decide? Well, we're using the plus or minus 2 standard deviations for our action, where we take action. But there are other things that might happen to the process. Let's say we had a couple of outliers in our learning, in our training period, right, where we're learning about our process. We're going along. Let's say we're doing daily difference in temperature. Here it is, winter. We get a big freaking cold front. So we get a huge out of control point, negative. Because today minus yesterday is really cold, it's negative. And then it comes along and it's back into kind of control. But that one data point that's way out is going to screw up our standard deviation, right? And then we're locking that in for the whole semester, but the training period, it was unreasonably big, right? That didn't reflect the process that was in control because we had an outlier. How would we determine that? Well, one of these rules, and this, I guess, Western Electric is the company that did this first, so the ASTM gives them credit. It says the Western Electric rules. So there's a whole bunch of rules here that you could use to determine if something is in control. And it says for standard deviation, let's see. Yeah, 15, rule number 2 here. 15 consecutive values are all within plus or minus 1 sigma on either side of the center line. So it's saying that our standard deviation is too wide. So it's not always about being outside the action limit. This rule says if you go then for 15, the next 15 measurements, and not one of those 15 goes outside of 1 sigma, then you don't have realistic limits. Your control limits aren't right. And so you need to reset your standard deviation. So it's not always about moving the mean. It could also be about getting an accurate standard deviation so that you know what your process is capable of. So that's it. That's one of the Western Electric rules. And so this is implemented in Minitab, again, the statistical control package. You could do all this in Excel, and that's what I'm teaching you guys to do. But in the stat packages, they have a menu item for control charts. So stat, control charts, variable charts for individuals, and you get the data. It's here in the notes for you. But once you do all of this, then you can set your rules. You pick the rules that you want. These are the Western Electric rules from that ASTM. Let's zoom in. So here they are. And I've got the menu item to perform all tests for special causes. So it's applying every one of these tests, which is not a good idea. We'll talk about that. But that's in the ASTM, those are the Western Electric rules, and here they are. K points in a row on the same side of the center line. Well, that says 9 over here. So you can adjust K for each one of those rules. And this gives you the freedom to pick your process and the thing that you're worried about. The thing that's really going to, let's say your check sample is a particular chemical compound, but that chemical compound happens to be thermally unstable. So it may not be the process that's changing, it may be the chemical compound. And so you may be worried more about the low side than the high side, okay? And so then you do the process and all of a sudden it starts to creep low. And you had 9 consecutive values that were on the same side of the center line. It's starting to creep low, and so you want to go ahead and refresh your chemical compound, run it again, and if it falls closer to the center line, then you're ready to go again. It wasn't the instrument, wasn't the calibration, it was your sample. So there's reasons, specific reasons to your process to pick 1 or 2 of these rules. If you pick all of these, then you've got a problem. And I'll show you why. Okay. But here's what Minitab produces for the control chart. It puts the points in red if they're out of control automatically, and it puts a little number beside it, and the numbers are in the session log. That's the second thing that's good about using a statistical control package like Minitab, is that it has this session log, which is your backup records for everything you did. So you can go in and change your formula in Excel, and Excel doesn't keep track of it. but Minitab does. So if you do anything in Minitab, it's like a tattletale running total of everything you did. Like if you go in and you change the data point or whatever, it'll tattle on you, right? That's what we want in forensics, right? We want a file that says, what did this analyst do? They came in, they redid this chart, they changed the axes to whatever, and it's all logged in the session log. And that's neat because then that's a subpoenaable record, and they can say, you falsified the data. It's like, nope, look at the log. I didn't do anything. I couldn't have. If I did anything in this package, it would have said so. And so then it's your backup. Okay, so here's those rules. 7, and look, 7's not outside the red line, but it's showing that it's out of control. So we can go into the session log and see. And here it says test number 1 was outside the deal, but 7, 15 points within 1 standard deviation of the center line. And see, it's looking for you. So you don't have to, so see here, this is apparently the center line, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you get to 14, and then that's the 15th one, and it flagged it. Okay. So the reason you don't want to include all of those tests is because you're going to waste time and money. The Kanban's too easy. The flags are popping up all the time, and so you don't want to empower all of those tests. You want to pick the ones that are relevant to your process, and the ones that are going to identify the thing that needs to be changed. So your control charts, without the little green box, but the green data. So the green box, your control chart should look just like this. It should have the green data, the black data, the red, orange, and green lines. The dates should be sideways like this. And it should skip 7 days so that it's every Monday or whatever that you want to do. But that way, I like it every Monday all the way along. And so that we can kind of see this is a week of data, this is a week of data, this is a week of data. Or if you don't plot the weekends, just do 5 every 5 days. But it's nice to have Monday be the date that's marked, and then we know. Okay. And so then every data point, you don't have to have these big red triangles. That'd be hard to sort of do automatically. But every data point that's beyond the action limit needs to have action, and our minimum action is to make a log entry. So this is what your spreadsheet will look like after 15 days. Some people are already starting to work on this. You can kind of go through the tabs and see who's got a whole lot of stuff on their page, and you can copy them. You can't copy their data, but look at their format, right? You're like, oh, I like that. That looks nice. It doesn't have to be all fancy, but I'm not going to be upset if it is a little fancy, but don't make it so fancy that it's like distracting. Just clean it up, make it look nice. But yeah, go through, because what is that? Is that realistic? Yeah, absolutely, it's realistic. You need to write a new report for a new agency or whatever. You ask them, what other labs, report to you? And then you call those labs. Hey, can you send me some example reports so that I know that they're getting from us a similar formatted report than what they're getting from you? And they're like, yeah, sure. Here's the last 2 months. And then you look at their format, and guess what you do? You copy the format. Yeah. And so it's a totally different mindset than the other writing component classes that we do. Okay. Now you need to use your own text. And don't get AI to write it. AI sounds crummy. Like maybe in the future it'll be something that could fool me, but I can tell. It sounds like a marketing executive is writing. Okay, so just write your own words. It's not it's like a 3 or 4 page thing. It's not a report that's this big. Okay, so hurrah for that. And then, but then your spreadsheet data, what we're talking about right now, is just format it nicely. Okay, and so kind of poke around, see what people have got. You don't need to do your chart yet. Okay, wait for a while. Wait for 15 days. Just start collecting your data. And so you have this training period, and then at the end of 15 days, you calculate the mean and standard deviation. Look at this blue box. I've got more data down here, but I don't care. It's only the first 15 days that I can use for the standard deviation and for the average. Okay. So that's something that people have messed up in the past. And then you create 4 more columns. Well, 4 more columns. 5 more columns. You have the mean column. So this mean is just that measured mean all the way down the same number. This is a little clunky, but I don't know an easier way to do it. Okay, maybe you know of an easier way to do it. I mean, you could have it like a separate little table with just 2 data points in it, but still. This is the mean column. This is this column plus 1 sigma. This is this column minus 1 sigma. So those are your watch limits. This is this column plus 2 sigma, and this is this column minus 2 sigma. And so you have, these are your green line, your orange lines, and your red lines, these columns here. Okay, so your data column bounces up and down. You plot that. You plot all 5 of these other lines. You go in and edit their colors so that you have the green mean and the orange watch and the red action lines. Get rid of the markers on those, obviously, because it's just a big distraction. It looks like you did it with a crayon. Okay, so get rid of the markers, make the line color red, orange, or green, and that's what you end up with. Now, let's go ahead and use the Boolean logic. Okay, that's the if-then statements and things to come up with our actions over here, or alerts, I would say. And so let's use if-then statements, and you can use text in these things. Now, this is a good way to do it, but there's a better way to do it. But anyway, this one uses the or function, which is kind of neat. If either this or that is true, then do this. Okay, so the way the if-then statement works is if this right here is true, then do this, which is between the first 2 commas, this first comma and the second comma, else this. Now, the else is blank. It just has 2 quotes, so it's empty. It doesn't do anything. So it's saying, if this is true, then write, quote, beyond action level. If it's not true, that's what's else. If, then else. If it's this, then this. Else, do the other thing. The other thing is nothing. Okay, 2 quotes with nothing in between. So that's good, and that's what gives us this right here, beyond action level, right? But this is better. It's a little bit longer. Oh, and the or thing is kind of cool, right? So it says, or will produce true if the first is true or the second is true. So that's kind of nice. You get to use a Boolean or gate. But this is even better. It has a nested if. So look, there's 2 ifs. So we're saying if D8 is greater than H8, so here's D8, here's our data, is greater than the plus 2S action, okay, then say above action level, that's in quotes, so it's going to put that text in the cell, else, then we have another if. So if it's not above, then do another if. If it's less than I8, I8 is the minus 2S, if D is less than I8, then right below the action level, else do nothing. So the do nothing, the only way you can get to that do nothing is it's not above and it's not below. So it's within. So we do nothing if it's within control. If it's above, we write above. If it's below, we write below. So that's great. And then that'll just show up automatically in your table, and you can look at that and go, oh, I've got something on February 16th. I need to go on the internet, or if I'm tracking my, I don't know, daily change in weight or something, I can say, what happened on the 16th? Oh, yeah, that was the day I had the flu. And so that's why you need something researchable. And so here's the weather one. You know, it comes along. It says a cold front came through. They were measuring something in the building, right? And so then this was below. So the maintenance was being performed on the building. And then this was above, higher than usual building use on this day. So maybe it was people, I don't know. But it's something researchable. If you do research online, put the URL in your table so I can see. You don't need, well, sometimes the URLs are really long, but that's okay. It's not that big a deal. Okay, so this is the format of your control chart. It should look just like this, without this green box. You don't have to draw that green box on there. There is one thing that journals discourage, and therefore I don't like, and it's this. It's in the checklist. Excel by default puts this outside bounding box on it, okay? So there'll be a box around the whole chart, and I will take off points for that. And that's, it says take off bounding box, okay? So this outside box, so get rid of that. So cut that out, okay? But I have people that are so paranoid about this, they're like, they'll take this one out. Okay, no, leave that one. Leave that one. That's around your data. This one's good. Good box. Bad box. Simple enough. Okay, so keep the good box, get rid of the bad box. Excel just does that, and I don't like it, and neither do the journals. Not that you're really publishing this for the journal, but it's unnecessary. You don't need it there, so get rid of it. So that's the box I'm talking about. You'll see in the little assignment checklist, it'll have all of the different things, and that's one of the things. It says the outside boundary box needs to be eliminated. Okay. And so then every data point beyond the action limit must trigger an action. The minimum action is to make a log entry. Okay, and this is again the discrete data, and the reason we don't want to use data that looks like this is because we're using Gaussian statistics, normal distributions, and these are not normally distributed because they're not continuous. The normal distribution is based upon the idea that you have continuous data along that axis, and if you don't have continuous data, you need to use a different kind of distribution. And then trending data is not in control, so this will be temperature, or whatever it says, daily change in flow rate, but it's trending up, and so that's not in control. A control variable should be the same throughout time, up and down across a mean. And so we could take the daily difference, and essentially we're taking the derivative, right? What's the derivative? It's the slope of the data, and the slope looks pretty constant. And so we're really just plotting the derivative of that data, and we're seeing it's constant. Now we can automate this process because it's pretty tedious, right? To go in and take a little data point and go into the spreadsheet, add it, whatever, and then look at the things like that. And so we can monitor this thing continuously using these little control charts. This is a circular chart recorder, and it measures relative humidity and temperature. So like you might have this in your lab if that was a deal that could swing your whole process. Like this building is so crazy. We need one of these, right? So you do analysis one day and they're doing maintenance and it's really hot in here, and then you do analysis the other day and it's really cold. That may swing your whole system. And that's a whole month of data on this disk. That turns really slowly. It takes 1 month to go all the way around. But you could see there'd be a record if there was an excursion in the room overnight. Like you come in and maybe they cut power overnight. They did some work on the street lights or something, and they come back in and the power's back on, the AC's back on, but you saw that there was an excursion. Like, oh, something's wrong. So 1 rotation per month tells the day the system went out of control. And this one's $960 on Granger. Now you guys with your budget may think that's a lot of money. Okay, that's not a lot of money. That's insulting. I didn't mean to be insulting, but it's $960 is, that's a chunk, right? But you're, as a forensic scientist, the median salary is around $34 an hour. And so this costs the company, because they got to pay the employer taxes and benefits or whatever, it might cost them $55 an hour for you. So that's their cost. And so this would be paid for. To break even would be 17 hours. So it's not a big cost, in terms of your time. So if it saves the employee more than 17 hours of time over the year, or however many years this thing works, they're going to get their money back real easily. Here's another one. This is a 3-channel one for $1,600. So it's beautiful, red, green, black, it's got all kinds of things on there. Now this really is just for process monitoring. It's not a control chart, but you could take this data out. It's logged. You could pull it into a computer. You could put it on a control chart and see. Okay. And this one, again, it's only 29 hours of labor break even. So It's not too bad. Yeah. Labor is always our most expensive thing. So anything that can save the employee's time is what we need to do. Okay. So that's the most expensive thing, even at a university campus. So all the staff, all the faculty, all the support services and everything, that's where a chunk of our budget, that's the major chunk of our budget. Okay, here's the data audit thing. That's my little piece right here. And not every time is it an audit like this one. I came back in to like find one to do a cut and paste, and then I noticed the formulas weren't right. So I put in here just yesterday, your daily difference formulas are missing, and there's some issues with that. So go in and check on. So if you see my little comments pop up here, take action. You know, that's not always losing points. Like I didn't take points off on this one because I did the data audit, and that one was worth points. I kind of warned people on last Thursday that I was going to do that over the weekend. And but this one was just, I happened to be in there, and I happened to look at the formulas, and so go in and check those formulas. It'll be good. And then if this gets in the way, because you're going to want your statistics columns, just select the whole thing, get on the edge, and drag it over here, and let go. And then it'll just push it over to the right, and then I can go find it. Don't like put it down below the data, because I'll be looking, where the heck is my box, you know? Put a box around it if you want, you know, like DW right here, and so it'll be fine. It's your spreadsheet, and have some fun with it within reason. Don't be ridiculous. Okay. So that's all I have for today. Again, just really emphasizing that point of statistical process control. Ideally, we have the process tell us when it's feeling pain, when it's not behaving in a normal random variation, and that saves us money, and it keeps our standard deviation as small as possible, because we're not always turning the knobs. If we introduce too many knob turners in the process, we just widen our standard deviation. And we'll say, yeah, the process is never out of control. Yeah, because your control limits are too wide. Yeah, and your variability is bouncing all over the place. And then you run into trouble with that process capability term, the Six Sigma term, and you're behaving like the trainee, not the forensic chemist, because your standard deviation is way too wide. Lots of false negatives, lots of false positives. We don't want that. Cool. So again, you can move my audit around. And if you see complete, that just means no points were lost. So you passed your audit. So that's cool. And it's good to introduce that terminology, because a data audit is something you'll have to go through. All right. See you next time.